Deep beneath the surface of reality, there is a law so unbreakable, so absolute, we've rarely questioned it. Time moves forward, always. Seconds become minutes. Ashes don't become trees. The dead don't rise. But why? In a universe where galaxies collide in elegant chaos and black holes rewrite space itself, why is time the one thing that only ever flows in one direction? Could it be an illusion, a glitch, or terrifying feature of our cosmic prison? And here's the real question. What if this isn't the way time works everywhere? What if our universe is the exception, not the rule? Subscribe if you've ever felt like time is racing ahead, because together we're about to slow it down, turn it inside out, and uncover the unsettling secrets of why time may knit. Begins with something so ordinary we barely notice it. A glass falling from the table, hitting the ground and shattering into a dozen jagged pieces. But have you ever seen that moment play in reverse? The shards rising, reassembling, floating neatly back onto the table. It feels wrong, unnatural, and yet, the laws of physics, the deepest, most sacred equations that govern our universe, wouldn't actually mind. They don't care whether time runs forward or backward. That revelation, first articulated nearly a century ago by the British physicist Arthur Eddington, is more than just a scientific curiosity. It's a philosophical earthquake. In 1927, Eddington gave this puzzle a name, the arrow of time, a poetic metaphor for something we all experience but cannot explain. Time flows, it points somewhere, and unlike space, unlike matter, unlike almost every other aspect of nature, it only goes one way. But why? Why do we experience life as a sequence of unidirectional moments, childhood, adulthood, aging, death, when the math underneath it all seems to allow for both directions equally? In Eddington's own words, if your theories are found to be against the second law of thermodynamics, I can give you no hope. He was referring to entropy, the hidden engine behind time's relentless march forward. We'll get there. But here, in this dimly lit study almost 100 years ago, Eddington planted the seed of something far stranger, that maybe time's arrow isn't a law of nature, but an illusion of perspective. Imagine for a moment, you wake up tomorrow, and everything feels off. The sun rises in the west. People walk backward. Words unspeak themselves. You're not dreaming. You're simply watching the film of reality played in reverse. It's disorienting, but not impossible. Because fundamentally, Newton's equations, Einstein's relativity, and even Schrödinger's quantum world don't forbid it. So why don't we live like that? Why is forward the only gear we seem to have? To understand that, we must confront the fragile veil between our experience of time and time itself. Consider this: the difference between a movie and a photograph isn't the medium, it's the sequence. We believe in time's flow because we remember moments stacked in a particular order. But what if our minds are simply projecting a narrative onto still frames? Think of your brain like a record player, not creating time, but reading it from the grooves etched into reality. If the grooves were reversed, would the song sound the same? Here's where the illusion gets personal. You've likely felt it, that haunting sensation that time is slipping faster with age. Childhood summers felt eternal. Now, years vanish like sparks in the wind. Is that physics or psychology? Is it entropy, ... or emotion? We are not passive passengers of time. We are co-authors of its perception. But perception, as any neuroscientist will tell you, is not always trustworthy. In 1957, A patient known only as HM underwent brain surgery to relieve seizures. The operation damaged a region called the hippocampus, and with it, his ability to form new memories. For the rest of his life, he existed in a frozen present. A man without a future, without a past, without time. If our sense of time can be shattered by a scalpel, what does that say about its objectivity? This is the first crack in the foundation. The first hint that time's arrow may not be pointing forward because it must, but because we are built to see it that way. In the next chapter, we'll dive into entropy, the mysterious law that supposedly explains why time flows. But entropy is a shadowy figure. It measures chaos, disorder, decay, and yet it hides. A riddle that scientists have never fully solved. Why was the universe ever in order to begin with? But before we go there, take a moment. Close your eyes. Picture your most vivid memory, your first love, the smell of a childhood home, the final goodbye of someone you lost. That moment lives in the past, and yet you can still feel it, almost touch it. Could it be that the past isn't gone? Could it be that we've misunderstood what time even is? Ever let us go in the heart of 19th century Vienna, as snow dusted the cobblestone streets and gas lamps flickered against laboratory windows? A quiet revolution was brewing, one that would define the future of physics and time itself. Ludwig Boltzmann, a restless and tormented genius, stared into the equations he had shaped from the chaos of thermodynamics. He had a problem. A simple, terrifying question. Why does time move forward? And his answer, buried deep in statistical mechanics, came in a single word: entropy. Entropy is not a force, not a field. It's a measure of disorder, of probability, of how jumbled and chaotic a system becomes over time. It's why a hot cup of coffee cools, why smoke spreads in the air but never compresses itself back, why life decays and stars die. The second law of thermodynamics states it plainly. In an isolated system, entropy will never decrease. It always increases, always. That's why time has an arrow, Boltzmann claimed. The future is just the direction where entropy climbs. But this answer only raises deeper questions. Why should entropy have started low to begin with? Why did the universe 13.8 billion years ago begin in a state of almost perfect order? Imagine dropping a deck of cards. The odds they'll land in the exact sequence you began with, nearly zero. And yet the early universe, right after the Big Bang, was like a cosmic deck, neatly stacked. How, we don't know. This is the paradox physicist Roger Penrose spent decades wrestling with. If entropy must always increase, and the universe is now in a state of growing disorder, then its beginning must have been astonishingly precise, a moment of clarity before the descent into chaos. And yet, that moment violates our understanding of probability. It's as if the universe began not with randomness, but with a whisper of intention. Boltzmann's equations were brilliant, but controversial. His ideas were mocked, dismissed, even vilified. In 1906, exhausted and ostracized, he took his own life. Decades later, those same equations would become the backbone of modern cosmology. But Boltzmann never lived to see time's arrow stamped across the sky. Entropy became a god of decay. But entropy does not cause time to flow. It marks the direction we call forward. Here's the twist. The laws of physics, Newton's motion, Maxwell's electromagnetism, Schwanger's quantum mechanics are all time-symmetric. They work perfectly in reverse. A falling apple obeys the same equations whether it's going down or floating up. In the math, the past and future are mirrors. So again we ask, what's actually pushing us forward? Could it be nothing at all? Some physicists now believe that entropy is only half the story, that the arrow of time isn't a fundamental law, but an emergent illusion, a kind of cosmic average rising from statistical tendencies, not hardwired truth. Let's test that idea. Imagine a box filled with gas. Shake it. The particles swirl chaotically, high entropy. Now compress that gas to one corner, low entropy. Did time just reverse in a lab? Yes, for a moment. But in reality, it took energy, intervention, design, because entropy may describe the likely path, but not the only one. And in quantum systems, where probability reigns supreme, entropy can fluctuate, even reverse, in brief, improbable moments. In 2019, scientists at the Moscow Institute of Physics and Technology used a quantum computer to simulate a reversal of entropy. For a tiny fraction of a second, time seemed to run backward. It wasn't real-time travel, but it hinted at something shocking. Time's direction might not be a universal law, but a local tendency. So here's the question we now face. If time's arrow is tied to entropy, and entropy is probabilistic, could time itself be a kind of illusion of scale? A large-scale consequence of billions of tiny, random events? If so, then, somewhere out there in the cold, deep vacuum of space, could entropy run in reverse? Could time? And if you were born in such a place, how would you even know? Would you remember the future? In the world of theoretical physics, some ideas are so radical, they don't just stretch the fabric of reality, they threaten to unravel it. Time crystals are one of those ideas. In 2012, Nobel Prize-winning physicist Frank Wilczek proposed something that sounded like science fiction, a phase of matter that moves forever without using energy, a structure that pulses not in space, but in time, a kind of crystal, not frozen in geometry, but locked in a never-ending rhythm, endlessly repeating like the ticking of a cosmic metronome. A time crystal. It violated everything we thought we knew about thermodynamics, a system in perpetual motion, without consuming energy. It echoed with forbidden words: perpetual motion machine, free energy, time loop. But Wilczek's math held, and others began to investigate. Years passed. Skeptics called it beautiful nonsense. But then, in 2021, something extraordinary happened. Google's quantum computing team, in collaboration with physicists at Stanford and Princeton, used their superconducting quantum processor, Sycamore, to create what appeared to be the world's first genuine time crystal. Inside this quantum machine, qubits flipped back and forth in perfect cycles, indefinitely, without losing energy, a behavior impossible in any conventional system. Time crystals were no longer theoretical. They were real. And that changed everything, because for the first time, we had created something that defied the traditional arrow of time. These systems weren't moving forward through entropy. They weren't decaying. They weren't stable in the way ordinary matter is stable. They were oscillating in a dimension we had assumed only flowed one way. But what exactly are time crystals? To understand them, think of a snowflake. It has a repeating structure in space, a spatial crystal. But a time crystal repeats in time, not because it's vibrating or being driven like a clock, but because its very ground state, its lowest energy condition, is rhythmic. It's as if time itself is baked into the matter's identity. In classical systems, this behavior would be impossible. Entropy would eventually eat away the rhythm. But in quantum systems, where uncertainty reigns and particles exist in a haze of probability, these cycles can be preserved, protected, by something called many-body localization. It's like shielding a flame from the wind using the complexity of the flame itself. Time crystals are not machines, or portals, or clocks, but they offer something more profound, a crack in the armor of time's irreversibility. They prove that, under very specific, very weird conditions, time's flow can be tamed. But what does this mean for the rest of us? Could time crystals allow us to build systems that remember the future? Could they be used to store information outside traditional timelines? Some researchers are exploring time crystals as the foundation for next-generation quantum memory, not just for computing, but for redefining how we think about duration, repetition, and permanence. More unsettling is this: if we can create time crystals in a lab, then nature, vast and unsupervised, may have created them already. Somewhere in the deep fabric of the universe, could time crystals be forming naturally? Could they be the core of certain dark matter phenomena? Could entire regions of the cosmos be locked into time-repeating patterns we simply haven't recognized? And here's a question most scientists hesitate to ask. If time can repeat at the quantum level, could it loop at larger scales? Could consciousness, your very experience of now, be riding a loop you cannot detect? There's no evidence of this, but the mathematics whispers strange possibilities, and it forces us to confront something deeply uncomfortable. Maybe time isn't a straight road, or even a river. Maybe it's a pattern, a structure, a fractal that folds back on itself in ways our linear minds can't perceive. As Wilczek once said, the world is a strange place, and it's not obligated to make sense. Time crystals prove that our assumptions about time, its direction, its linearity, its decay, are not laws. They are expectations, and expectations in science are made to be broken. So what else could be out there if we've discovered the first loophole in time's rigidity? How many more might exist? And if we learn to control them, not just observe them, what doors might that unlock? Rewind the cosmos, beyond the stars, past the nebulae. Before galaxies had names, before matter had form, there was a moment so brief, so furious, that it birthed all of time as we know it. The first second of the universe. In that instant, the laws of physics were not settled. Time, space, energy, they were newborn forces, wrestling for dominance in a chaotic dance of unimaginable intensity. If we could stand on the edge of that moment, we wouldn't see light, we wouldn't see fire, we would see potential. The raw, unrefined furnace of existence. This is where time began, or so we believe. According to the standard cosmological model, the Big Bang wasn't an explosion in space. It was the expansion of space itself, and with it came time. Before that, there was no before, because before is a time-bound concept, and time hadn't yet arrived. But here's the twist. The laws that define our universe today, the ones that determine gravity, mass, electromagnetism, didn't exist during the universe's first heartbeat. They emerged from what physicists call symmetry breaking. Picture a pencil standing perfectly on its tip. In theory, it could fall in any direction. But the moment it tilts, the symmetry is broken. One direction is chosen, and all others are excluded. Our universe, in its first trillionth of a second, was like that pencil hovering in a perfect symmetry of possibilities. When it fell, it chose a specific direction for time, forward. But why that direction? Why not backward? This is the puzzle that haunts cosmologists at CERN and the Max Planck Institute. If the fundamental laws are mostly time-symmetric, indifferent to direction, then the choice of a forward-flowing time isn't dictated by physics, but perhaps by chance, a coin toss, a random fluctuation, a cosmic accident. Dr. Marina Koren, a theoretical physicist working at the European Organization for Nuclear Research, describes the early universe as a storm of symmetry collapses, forces separated, quarks condensed, time stabilized, but she admits we don't yet know why time settled the way it did. The equations work in reverse just fine. It's a humbling idea that everything we've built, every civilization that's ever risen or fallen, exists because time happened to lean one way instead of the other. But what if the coin had landed differently? Some theories suggest that it did. One bold hypothesis is that the Big Bang didn't just create our universe, it created two mirror universes, born from the same singularity, but moving in opposite directions in time. In this view, what we see is the past, they see is the future. And somewhere beyond our observable horizon, that other universe is aging in reverse. Not as science fiction, but as symmetry. This model, called the Janus cosmological model, named after the Roman god with two faces, offers an elegant solution to the low-entropy paradox. If two universes emerged from the same point, then each could start in a low-entropy state and diverge, giving the illusion of time flowing forward in both. But they aren't forward to each other. They're in perfect opposition. What would such a universe look like? Galaxies that unform, stars that reassemble from gas, dead civilizations returning to life, a world where memory builds toward birth, not death. And if we could somehow cross the barrier, what would we see? Would we experience our own death in reverse? Would we age backward? Would we even survive the transition? These are unanswerable questions, for now, but they hint at a chilling possibility that time's arrow is not a universal truth, but a regional dialect of physics, one shaped in the chaos of a baby universe struggling to find its identity in the laboratories of Geneva and Munich. Particle physicists smash atoms together in the hope of glimpsing the earliest moments, trying to recreate the first trillionths of a second. After time switched on, they watch for hints, for symmetry violations, for decay patterns that whisper secrets of the beginning. But the clock is silent. The cosmos does not yield its origin easily. Still, we search, because in that search is the chance to understand something breathtaking, that our experience of time, of movement, of memory, of meaning, is not guaranteed. It is granted, and that grant may have been one flip of a coin, away from being something else entirely. In the grand halls of theoretical physics, few ideas carry the weight or the unease of the mirror universe. Imagine this, a cosmos, born not alone, but with a twin, not side by side, but inverted, not light years apart, but flipped. In time, in the moments after the Big Bang, when reality itself crystallized into form, some physicists believe that our universe may have split, not just in space, but in temporal orientation. One, expanding forward, what we call the future. The other, backward, what, to us, would look like a universe unwinding. This isn't science fiction. It's the essence of the Janus point hypothesis. a radical but mathematically grounded theory proposed by physicist Dr. Julian Barber. According to Barber, the Big Bang wasn't the beginning of time. It was the middle. Picture a point of perfect order, a cosmic 0 point, from which two symmetrical universes explode in opposite time directions. Like a firework, not with one stream of sparks, but with two. You are in one. The other is out there, beyond any signal we can receive. To the inhabitants of that other universe, if they exist, time would feel just as normal as it does to us. They would experience birth, aging, memory, death. But their forward is our backward. They would see our future as their past, our end as their beginning. Let that settle in. What if our death, the heat death of the cosmos, the entropy-maxed void, billions of years from now, is to them a dawn? What if we are living in their history and they in ours? Dr. Sean Carroll, cosmologist at Caltech, has explored this idea in his work on the thermodynamic arrow of time. He agrees, if the universe can emerge from a low-entropy starting point, there's no reason it couldn't split into two opposing time flows. The math works. The challenge is observational. We can't see past our cosmic horizon, and they, if they exist, can't see past theirs. We are sealed from one another by time. Still, clues may lie in the subtle fingerprints of early cosmology. Slight asymmetries in the cosmic microwave background, fluctuations in particle decay, hints that something on the other side is tugging at our universe like a shadow, pulling on a curtain. But let's take this further. If mirror universes are real, then somewhere in that inverted world, there may be a version of you, not a clone, not an alternate self, but a being whose birth corresponds to your death, whose thoughts are shaped not by your decisions, but by your outcomes. A version of humanity not marching forward, but retreating from the end. Could such a civilization exist? And more hauntingly, would they ever know the truth? Their scientists might discover, just as ours have, that time is an emergent property, that entropy guides their experience, that the cosmos began in ordered symmetry and decays toward chaos. But for them, that decay is our genesis. It's a terrifyingly elegant symmetry. But what does it mean for us? If time is not absolute, if its direction is relative, like motion or perspective, then our reality is not the only possible one. There may be other ways for existence to unfold, other minds shaped by a different flow, and perhaps, just perhaps, other laws, because in a universe flowing backward, some of our most fundamental concepts might break. Causality, choice, identity. Would their concept of memory be based on what we call prophecy? Would they predict the past instead of remembering it? And if, somehow, a window opened between the two universes, what would we see? Would it be chaos, disorder, an impossible ballet of time collisions? Or would we see ourselves, staring back through the mirror? The idea may seem distant, impossible to test, but it carries consequences. If time can flow both ways, then our arrow is not the only one. And that means everything we assume about life, about fate, about endings, might be local truths, not universal ones. It's a humbling reminder that our experience is not sacred, it's conditional, fragile, born of a moment we never witnessed, shaped by laws we don't fully understand, and yet it is ours. As we move forward, ever forward, we do so not as the masters of time, but as its passengers, passengers who may have siblings riding in reverse. Somewhere out there, a civilization, maybe watching the stars unfold, galaxies coalescing from void, order emerging from ash, birth rising from death. And they may be asking the same question we are right now. What lies on the other side of time? What if the flow of time isn't real? What if it's not the universe that moves but our minds? Every moment you remember is a frame, a snapshot, your first bike ride, a heartbreak, the final words of someone you loved. These are not films playing across a timeline. They are frozen pictures, and you are the projector. This idea, as unnerving as it is beautiful, lies at the intersection of neuroscience and physics. And it begins with a question few dare to ask. Do we experience time because it exists? Or does time exist because we experience it? In the corridors of MIT's Department of Brain and Cognitive Sciences, Dr. Anna Wexler walks us through the most bizarre experiment you've likely never heard of. Her team showed participants sequences of still images, some logical, some scrambled, and monitored their brain activity. The results? The brain doesn't passively record time. It constructs it, piece by piece. Like a story, your perception of flowing time is the brain stitching together what it calls temporal binding. It doesn't receive reality in a straight line. It infers causality and order based on memory, prediction, and pattern. Think about that. You're not living in time. You're guessing it. And this gets even stranger when we meet the case of Dr. Anna Jablonski, not a researcher, but a patient. In 2003, after a car crash in Warsaw, Anna suffered trauma to her hippocampus, the region of the brain critical for encoding new memories. From that day on, she lived in a 30-second loop. She could hold a conversation, then forget it, eat lunch, and forget she aged, changed, existed. But for her, the river of time had frozen. Her case, like that of the famous patient. HM taught neuroscientists that memory isn't just a feature of consciousness. It is consciousness. Without memory, there is no past. Without anticipation, there is no future. So then what is time, really? Some researchers now believe that consciousness creates a kind of mental time travel, that our sense of self is a flickering illusion made of remembered events, bound together by imagined continuity, a slideshow that we mistake for a film. In 2014, psychologist Dr. Dean Buonomano published Your Brain is a Time Machine, arguing that the brain's ability to track time evolved not for accuracy, but survival. We needed to know when to hunt, when to flee, when the seasons changed. The flow of time was never objective. It was adaptive, and like all adaptations, it can be fooled. Consider déjà vu, that eerie sensation that you've lived this moment before. It isn't magic. It's a glitch in the brain's timing circuits. A brief misfire that makes the present feel like memory. It reveals just how fragile our temporal compass really is. If time was something we observed, déjà vu would make no sense. But if time is something we build, then every misfire, every distortion, every dream, every trauma, reshapes how we experience its flow. It's here we reach a sobering conclusion. We may not live in time. We may live in memory. And if that's true, then the arrow of time isn't pointing forward because the universe demands it, but because we are wired to believe it does, which begs the question, if memory defines time, and memory can be erased, altered, or lost, can time be rewritten, not physically but subjectively? Could trauma stretch time? Could wonder slow it down? Psychologist Mark Whitman has studied how emotional states alter time perception. Fear compresses time, boredom dilates it, awe seems to pause it. Time is elastic. not in space-time, but in the mind. In extreme cases, such as near experiences, individuals report entire lifetimes flashing by in seconds, as if the mind, facing its own extinction, abandons the timeline altogether. This isn't just poetic, it's biological. Your brain doesn't carry time like a clock. It carries it like a map, a shifting constellation of memories, predictions. An identity, remove the landmarks, and you lose the map. Remove the map, and time disappears. So what does this mean for our search for time's true nature? It means we may be biased. Every experiment, every theory, every observation we've ever made passes through the filter of human cognition. We are temporal, creatures trying to decode time, using tools built by memory, guided by prediction, rooted in emotion. We may never see time for what it is, only for what it feels like. So pause now. Look around. Listen to the hum of your environment. Notice your breathing, your heartbeat. Ask yourself, is time passing? Or are you simply changing? Are you flowing through time? Or is time flowing through you? And if memory shapes reality, what happens when memory fades? What happens when the projector goes dark? For centuries, humans have dreamt of escaping time's grip, slipping into the past, leaping into the future, rewriting fate. Time travel is one of the oldest desires etched into our myths, our literature, our science fiction. But here's the truth. It's not entirely fantasy, because deep in the fabric of physics, time travel is permitted. The question is, should it be? We begin with Einstein. His theory of general relativity doesn't just describe how mass warps space, it shows how mass also warps time. Near a black hole, time slows. In extreme cases, it can even appear to stop. But the real revelation came from the mathematics of space-time itself. Under certain conditions, the equations allow for what physicists call closed time-like curves, loops, paths, through space-time that return to their own origin in 1988. Physicist Kip Thorne, a name now synonymous with interstellar, demonstrated that, in theory, a traversable wormhole could allow time travel if one end of the wormhole experienced time dilation by moving at high speed or resting near a black hole, and the other didn't. The two ends could fall out of sync, step through one, and emerge in the past. But with that step comes a monster, the paradox. The most famous is the grandfather paradox. You go back in time, prevent your grandfather from meeting your grandmother, and thereby erase your own existence. But if you never existed, who stopped the meeting? Physics, so elegant, so precise, begins to twist in knots. Many scientists argue that paradoxes prove time travel is impossible. Nature, they say, must have some hidden law that protects causality. The universe will not allow contradictions, but others believe in consistency, that any journey into the past must be self-contained. You were always meant to go back. Your actions in the past already happened. You cannot change the timeline, only fulfill it. This is known as the Navikov self-consistency principle. In this view, the timeline is a loop, not broken, but sealed. Yet even this raises disturbing questions. If all time is fixed, if the past cannot be changed, then is the future also written? Are we free? Or are we passengers trapped in a four-dimensional sculpture we can never reshape? To find clarity, physicists turned to quantum mechanics, the realm of uncertainty. Some hoped that quantum theory, with its branching possibilities and observer-dependent outcomes, might rescue free will or offer escape routes through the timeline. in 2020. Researchers at the University of Queensland simulated time travel using quantum computers. Their experiment modeled a qubit, a quantum particle traveling back and interacting with its earlier self. The result, no paradox. The quantum system adapted, rerouting probabilities to maintain consistency. It was small, symbolic, but profound. Could quantum mechanics allow time travel, not by preventing paradoxes, but by absorbing them? Enter the many worlds interpretation. According to this controversial view, every quantum event creates a branching universe. If you travel back in time and change something, you don't alter your own history. You spawn a new one, a parallel reality, one where your grandfather never met your grandmother, and that version of you never existed. No paradox, just multiplication. But this theory carries its own cost, a staggering inflation of realities. Every choice, every possibility, forever spinning off into an endless multiverse. Time travel, in this context, becomes dimension hopping, not revisiting your past, but visiting a sibling world. And yet, we have no evidence, no messages from the future, no visitors from the past, no machines warping space-time, no footprints left behind by meddling travelers. If time travel is possible, why hasn't it happened? Some propose that time travel, like entropy, is asymmetrical. We can move forward, we do it every second, but the past may be sealed. The initial conditions of the universe may simply forbid loops. Others suggest a kind of chronological censorship, a principle proposed by physicist Matt Vis, that the universe, through subtle mechanisms, hides or destroys all time-traveling effects before they manifest. Maybe the past resists change, not with paradox, but with probability. But perhaps the more haunting answer is this: we're too early. Time travel might require technologies, energies, or understandings we haven't even imagined. Wormholes stabilized with exotic matter, machines that can twist space-time like ribbon, or quantum protocols that tunnel through the probabilistic fog of the universe. One day, far in the future, a civilization might master such forces. They may send signals backward, witness their own origins, even stand at the threshold of time's beginning. But until then, we wait, bound by a timeline we cannot bend. Still, the dream persists, because time travel is not just a scientific puzzle, it is a mirror reflecting our deepest desires to undo, to understand, to escape. It whispers of lost moments, second chances, future glories. So here's a question. If a time machine appeared in front of you right now, would you step inside? And if you could go anywhere, anywhen, where would you go? Look up. Every star you see is a memory. Even the sunlight warming your skin left the sun 8 minutes ago. The Andromeda galaxy, you're seeing it as it was over 2.5 million years in the past. In a cosmic sense, you have never seen the present, only echoes, only ghosts. This is the strange truth of physics. You are trapped inside a structure called your past light cone, the region of space-time from which light and information can reach you. Everything you observe, every flicker of light that enters your eyes, is already old. In this sense, we all live in the past. The idea of a light cone comes from Einstein's theory of relativity. It's not just a metaphor, it's geometry. At every point in space-time, there's a cone pointing backward in time, the past that can affect you, and a cone pointing forward, the future you can influence. Between those cones lies a forbidden zone, events you can neither reach nor be reached by They're elsewhere, untouchable, outside your now, and this structure shapes the very meaning of time to you. Now feels like a universal moment, but in physics, simultaneity is an illusion. According to Einstein, two observers moving at different speeds can disagree on whether events happened at the same time or in a different order entirely. Time is relative. This isn't just theoretical. In 1971, a pair of synchronized atomic clocks were flown around the world on commercial airliners. When compared with clocks left on Earth, the airborne clocks had ticked slightly slower, confirming time dilation predicted by relativity. But here's the twist. It also confirms that your present is not the same as someone else's. Even slight differences in motion or gravity cause time to shift. Your now is yours alone. So what happens when we apply this to the universe? Let's say a galaxy exploded 1 billion light years away. The light from that event is just arriving at Earth today. But from the galaxy's point of view, that explosion happened long ago. From your point of view, it's happening now. And for someone even farther out in space, it hasn't happened yet. One event, 3 different timelines. This means the universe doesn't experience time as a single flowing river. It experiences it as a vast landscape, a mosaic of events arranged not in sequence, but in location. A map of moments, not a line. You are not moving through time. You are revealing different regions of this map as you move through SPAC, and this revelation has profound consequences. Because if the universe is a timeless block, a 4-dimensional sculpture of space-time, then past, present, and future all coexist, eternally, permanently. Your childhood, your last breath, the last stars, final flicker, all equally real. All encoded in the cosmic structure, but we can only access a slice, the part within our light cone, which brings us to the edge of something eerie. If we only ever see the past, who's to say someone or something isn't seeing us the same way? Imagine an alien civilization on a planet 200 million light-years away. If they had a powerful enough telescope aimed at Earth, what would they see? Dinosaurs. They would be watching the Mesozoic era unfold in real time from their perspective. Our present is their deep past. Now flip it. If someone on Earth had a telescope that powerful aimed at their planet, we'd see their past. The whole universe becomes a time machine, not of motion, but of observation. This is not fantasy. It's fact. You exist not just in space, but inside a glowing shell of history. The farther you look, the older the image becomes. This leads to a chilling thought. Is anyone watching us? Right now, observing the past we've already forgotten. And further, could we ever look outside our past light cone? Could there be parts of the universe, or realities beyond it, that exist in ways we'll never detect, because light has not, and never will, reach us? Some physicists propose that these regions might not be part of our timeline at all. They may exist in completely disconnected temporal frames, flowing at different rates, or not flowing at all. If so, then our experience of time is more provincial than we ever imagined, a local dialect spoken only by the matter in our region of the universe. So next time you gaze into the night sky, remember, you're not looking at stars. You're looking at survivors, photons that traveled billions of years just to reach your eyes. Messages from the past, racing through a universe that may no longer resemble the place they left. And ask yourself, if the cosmos is a memory, what is the present, really? Is it a moving dot? or just the part of the map we happen to be reading. There is a place where the rules of time begin to unravel, a place where clocks stop ticking, events freeze, and the very concept of before and after collapses into me, NANGLESS. It's not a fantasy. It's a black hole at the center of our galaxy, 26,000 light-years away, lies a monster, a supermassive black hole named Sagittarius A, invisible to the eye, yet for 1,000,000 times the mass of our Sun. Around it, stars whip at speeds that defy comprehension. But near its edge, the event horizon, something stranger happens. Time begins to slow. To an outside observer, anything falling into a black hole appears to decelerate, as if sinking into syrup. Clocks tick slower. Light stretches to red. A falling object seems to freeze at the edge, eternally suspended in a silent farewell. But from the object's point of view, it falls normally. It passes the event horizon in seconds, and then the known laws of physics fall apart. This is not science fiction. It's the reality confirmed by general relativity. Gravity isn't just a force, it's a curvature of space-time. And near a black hole, that curvature becomes so extreme, it distorts time itself. We don't often think of time as something that can bend or break. But in the presence of immense gravity, it must. Time becomes elastic, directional, subjective, and this isn't limited to black holes. It happens subtly on Earth. Your head ages faster than your feet. If you live at sea level, you age slightly slower than someone living on a mountain. GPS satellites must account for time dilation to remain accurate. Otherwise, your phone would drift kilometers off course each day. But in a black hole, these effects go to extremes. Time stops for the outside world. Inside, it becomes undefined. What lies beyond the event horizon is one of the greatest mysteries in all of science. Some theories suggest a singularity, a point of infinite density, where matter and time are crushed into a zero-dimensional speck. But infinity is not a number. It's a signpost that our physics has reached its limit. Others propose a gentler solution, that black holes may harbor bridges to other regions of space-time, wormholes, portals, connections to other universes, or even to other times. But no one knows for sure, because once something crosses the event horizon, it cannot return. Not light, not data, not even information, or so we thought. That belief was challenged in the 1970s by Stephen Hawking. He proposed that black holes emit faint radiation due to quantum effects, a process now called Hawking radiation. Over immense timescales, this would cause black holes to evaporate. But this created a crisis. If black holes evaporate and disappear, what happens to the information they swallowed? Quantum mechanics demands that information is never destroyed. It can change form, but it cannot vanish. Yet general relativity says the contents of a black hole are lost forever. This contradiction between the two most successful theories in physics is known as the black hole information paradox, and it's more than a theoretical puzzle. Because if information is tied to entropy, and entropy defines the arrow of time, then the fate of information inside a black hole could determine whether time's direction is truly fundamental. In 2019, researchers using the Event Horizon telescope released the first image of a black hole's shadow, a glowing ring of plasma swirling around darkness. It was visual confirmation of what Einstein predicted over a century ago, but it was also a mirror, a glimpse into a realm where time is no longer linear, no longer trusted, Dr. Andrea Ghez who helped confirm the presence of Sagittarius A*, described watching stars near the black hole bend their trajectories in unnatural arcs. "You're not just looking at motion," she said. "You're watching gravity sculpt time. But it's not just black holes. In the earliest moments of the universe, near the Big Bang, the energy density was so high that time itself may not have existed in any meaningful way. There was no before, only potential, and at the end of time, the final moments of black hole evaporation, when Hawking radiation fades into silence, time may fracture again, dissolving into quantum uncertainty. It seems that at the extremes, at the borders of understanding, time is not a line, but a loop of riddles. And here's where it gets personal. If time can be bent, stretched, frozen, and erased, what does that say about us? Are we travelers, witnesses, or illusions? Could the sensation of time breaking down near death, during trauma, in deep meditation, be a faint echo of the same phenomena? Could black holes be showing us the true face of time, not as a river, but as a fabric, one that can tear, and if time can break, could it be mended? Or worse, could we fall through the cracks? Imagine a future so distant, numbers can't hold it, 1 trillion years. Then 1 trillion more. Stars are long gone. Galaxies have unraveled. Black holes have fizzled into quantum mist. Now, stretch that silence into infinity. This is the universe's final act, a realm scientists call heat death, a time not marked by clocks, but by stillness. When all usable energy is gone, no motion, no light, no change, no time. Because if nothing changes, does time still exist? The concept of heat death arises from the second law of thermodynamics. Entropy will always increase in an isolated system. Our universe is that system. And as entropy rises, the energy gradients that power everything, stars, winds, life, begin to flatten out. Eventually, everything that can happen will have happened, and then nothing, no chemistry, no heat, no physics left to play out. The universe enters thermal equilibrium, a state of maximum entropy, homogeneous, featureless, a vast expanse where every part is identical to every other, and with no events left to differentiate moments. Time itself loses its meaning. It doesn't stop. It becomes irrelevant. This is not a dystopian fantasy. It's the leading prediction of mainstream cosmology. A future so alien, it's hard to comprehend, not with fire and destruction, but with infinite boredom. We often picture the end of the universe as dramatic, collapsing in on itself, or exploding outward in chaos. But heat death is quieter, colder. It's the slow dying of novelty, and it may already be underway. Our current epoch, the Stelliferous era, is defined by stars and galaxies. But stars have a lifespan. Red dwarfs may last trillions of years, but even they will burn out. After that comes the degenerate era, ruled by white dwarfs, neutron stars, and black holes, silent monuments to what once was. But even these will decay through a process called proton decay, still hypothetical but widely considered. Even matter itself will dissolve. All that will remain are photons, neutrinos, and the fading embers of radiation and time. Well, it will be meaningless in a universe where nothing changes. This vision comes from some of the brightest minds in cosmology, including Roger Penrose, Freeman Dyson, and Lawrence Krauss. But not all agree. Some theories suggest the universe may undergo a big rip, where dark energy accelerates expansion until space-time itself tears apart. Others propose a big bounce where the universe collapses and re-expands in cycles. These scenarios avoid heat death, but they carry their own horrors. Still, heat death remains the most accepted fate. A cold, empty, eternal night. But the implications go far beyond physics. What does it mean for us? For meaning, for memory, for the story of life? If time eventually ceases to matter, then so do causality, change, and experience. Even the concept of before and after dissolves. And in a way, that means the universe doesn't end in fire. It ends in timelessness. And here's a stranger idea still. If time is bound to entropy, and entropy reaches a maximum, could time reverse? Could another low entropy fluctuation spark a new beginning? Some cosmologists believe that in an infinite timeline, rare events, even wildly improbable ones, become inevitable. Given enough time, order can re-emerge, not because it's likely, but because the universe has forever to wait. This leads to the idea of the Boltzmann brain, a fully formed conscious mind that randomly assembles out of quantum chaos. Statistically absurd, philosophically haunting. If a mind can emerge spontaneously from entropy, is it any less real than one that evolved? And if such a mind existed in the deep freeze of the future, what would it perceive? Would it feel time? Would it remember? These questions push the limits of science and identity. Because at its heart, the end of time isn't just about physics. It's about loneliness. It's about the end of witnessing. If there's no one left to experience change, does the universe still change? Does it still exist in any meaningful way? This echoes the old philosophical riddle. If a tree falls in a forest and no one is there to hear it, does it make a sound? If the universe dies and no one is left to count its final seconds, does time still tick, or has it already stopped? Some philosophers and physicists now question whether time was ever fundamental to begin with, that perhaps it's an emergent property of interactions, that where there is no interaction, there is no time. If that's true, then time will not end. It will simply vanish, and all that's left will be the memory of memory, the echo of echoes. So pause, just for a moment, and reflect on this. You are alive in the briefest flicker of a universe that has change, that has stars, that has time, and one day far beyond our reach. That flicker will fade, and in the silence that follows, time itself may go to sleep forever. Time, as we experience it, is a one-way street. Events unfold, entropy increases, memories accumulate. But what if that street isn't a law of nature, but a preference? And what if under just the right conditions, it could be reversed? In 2020, a team of researchers at the Moscow Institute of Physics and Technology did something remarkable. Using a quantum computer, they designed an experiment to simulate the reversal of time for a fraction of a second in a closed quantum system. They made entropy decrease. The effect wasn't visible. No glass unshattered, no broken egg reassembled, but at the level of quantum information, time's arrow bent. It wasn't a time machine. It didn't allow travel to the past, but it proved something profound, that under certain conditions, systems can appear to reverse time's flow. The arrow isn't fixed, it's emergent. To understand how this works, imagine entropy as a mountain slope. In most situations, objects roll downhill from order to disorder. But in the microscopic world of quantum mechanics, the mountain isn't solid. It's made of probabilities. And in rare cases, the ball can roll uphill, not because the Laws were broken, but because chance allowed it. These are called fluctuation theorems, rare events that defy the average behavior of thermodynamics. And in small enough systems, they don't just happen, they're expected. This means the arrow of time, which seems so absolute to us, may be a large-scale illusion, a byproduct of the universe's vastness. In the quantum realm, where particles blink in and out of coherence, time doesn't always flow forward. It flickers. So why don't we see this? Because we're too big. Our bodies, our memories, our cultures, all built on trillions of entangled particles. Entropy dominates our scale. The fluctuations that might reverse time in a quantum system are drowned in our macroscopic world. But that doesn't mean they're not real. And it begs a radical question. If time's direction is local, then could different regions of the universe have different arrows of time? Cosmologist Sean Carroll has proposed precisely this, that the low entropy beginning of our universe may not have been unique, that elsewhere, in pockets beyond our observable horizon, time may flow backward. From our point of view, to them, we are the ones running in reverse. It's possible. Carroll argues that our universe is just one part of a larger multiverse, a broader time-symmetric cosmos where entropy increases in both directions from a central low-entropy point, the so-called Janus point. From there, two universes expand, one forward in time, the other backward, both experiencing time as moving forward relative to themselves. Which one is correct? The answer may be both or neither. Because in a time-symmetric universe, direction becomes a matter of perspective, not law. Now consider this. If we could somehow step outside the universe, beyond space, beyond time, would we see both flows at once? Would the arrow of time dissolve into a still image, a single, four-dimensional sculpture with no true beginning or end? This idea is not new. Physicist Julian Barber has long argued that time doesn't exist at all, that what we perceive as flow is an illusion, that every moment past, present, and future already is, like frames on a film reel. In that model, reversing time is meaningless. There's no movement, only existence. But if we return to our lived experience, where time flows, choices matter, and death is real, the arrow is all we know. It gives life structure. It defines consequence. To reverse that arrow, even locally, would mean more than a scientific breakthrough. It would mean rewriting the story of causality. Imagine a world where entropy runs backward, ice spontaneously forming from lukewarm water, ashes condensing into logs, people growing younger, thoughts unthought, every cause becoming its effect. It's not just strange, it's horrifying, because we are built for forward time. Our biology, our psychology, our meaning, all entangled with entropy's march. To reverse it would not be time travel. It would be time annihilation. Yet the quantum world continues to hint that such reversals are possible, not on our scale, but deep beneath it. And here's a terrifying possibility. What if intelligence advanced, post-biological intelligence, found a way to control these fluctuations? What if there were civilizations, somewhere out there, that could reverse entropy locally, and thus manipulate time? Would they be able to watch their own histories, undo their mistakes? Would they live in loops? Would they escape the heat death of the universe by reversing its decay? Or would they disappear into timelines we can no longer follow? If time can be reversed, not in fantasy but in physics, then our grip on now is far weaker than we think. The arrow may be pointing forward only because we're standing on a hill that slopes that way, but hills can change, and in the quiet hum of a quantum machine, they already have. If you could step outside this universe, peel back the veil of space and time, what would you see? Maybe others, not stars, not galaxies, entire realities, infinite in number, each with its own laws, its own beginning, its own version of time. Welcome to the MULTIV. It's not just a science fiction dream. It's a legitimate, though deeply controversial possibility in modern physics. From cosmic inflation to string theory, many of our most successful models suggest that our universe is just one bubble in an eternal foam, a single timeline, drifting in a sea of timelines. But here's the twist. If the multiverse is real, then time itself may not be universal. Each universe could have its own clock, or none at all. In our universe, time flows from low entropy to high, from Big Bang to heat death. But what if, in another bubble, time never began? What if it runs backward, or sideways, or in a loop? Some regions may have no entropy at all, no arrow, no history, no direction. Others may experience time as a spatial dimension, accessible, navigable, rewritable. And still others may exist in a kind of timeless stasis, where events don't unfold but coexist, like frames in an eternal sculpture. We don't know, but the math allows it. In the theory of eternal inflation, quantum fluctuations cause space to expand unevenly, endlessly. Each fluctuation spawns a new bubble universe, disconnected from ours by a vast cosmic barrier. These bubbles can have different physical constants, different gravity, different particles, and yes, different time structures. This leads to a question so strange it sounds like madness. If a being could traverse the multiverse, would it feel time differently? In each universe it entered, what would now even mean? We assume time is linear, consistent, the same for all observers, everywhere. But Einstein shattered that illusion with relativity. Time depends on motion, on gravity, on context. The multiverse could take that relativity to an extreme. Time may not just vary, it may be fundamentally undefined, outside a given universe's context. This has staggering implications. Imagine a civilization, advanced enough to open portals between universes, a multiversal society. They would have to invent something inconceivable, a universal translator for time, a way to map one universe's clock to another's. But how? If two universes have no shared physics, no shared entropy, no shared light, how do you synchronize them? It may be impossible, and perhaps that's why we've never received a message from beyond. Not because no one is trying, but because time itself is incompatible, like trying to match a melody with a painting. Still, the concept fascinates physicists. In 2014, a team at the Perimeter Institute explored the possibility of multiversal entanglement, quantum connections between particles in separate universes. If true, it could offer a bridge not through space, but through time itself. But even if we never make contact, the idea challenges how we define the real world. Because if time is not universal, then neither is experience, neither is memory, neither is meaning. Each universe becomes its own story told in its own language of moments. And if some of those universes lack time altogether, then they lack sequence, they lack growth, they lack life, or do they? Could intelligence arise in a timeless universe? Could consciousness exist without duration? Some philosophers believe so, that awareness is not bound to time, but to pattern, that a static arrangement of information could, under the right interpretation, contain all the qualities of a thinking mind. A timeless being would not think through time. It would simply be a complete, unchanging expression of thought. It would perceive all moments at once. But we are not that. We are trapped in one bubble, one arrow, one story, and we measure it obsessively with watches, with calendars, with heartbeat and breath. We build our lives around clocks, even though the cosmos may not have one. It's a haunting contrast in a universe that may be one of infinite variations. We act as though time is absolute, immutable, sacred, but maybe it's just ours, a local illusion, a dialect of motion, a shadow cast by entropy onto the fabric of experience. And if we could peer across the multiverse, we might see a gallery of clocks ticking at different rates in different directions, or not ticking at all. So here's the question. If you could leave this universe and enter another, where time was broken, looped, frozen, or free, would you still feel like would your identity survive? Or is the self just another echo of the clock? Time doesn't just shape galaxies, it shapes us. It creases our skin, weakens our muscles, clouds our memories. It takes children and makes them strangers to their younger selves. Time, to the human body, is a silent predator, and aging is its footprint. But what if aging isn't an inevitable march toward death, but a process we can interrupt? What if time's grip on our biology is weaker than we think? At Harvard Medical School, in a quiet lab filled with glowing petri dishes and humming centrifuges, Dr. David Sinclair studies this very question. For decades, he and his team have been exploring how cells age and whether that aging can be slowed, paused, or even reversed. His research doesn't just challenge biology, it challenges time itself, because aging, at its core, isn't about time, it's about entropy. Just as the universe slides from order to disorder, so do our cells. DNA breaks down, proteins misfold, communication between organelles falters. It's not a countdown, it's a collapse of structure. But entropy can be resisted. Sinclair's work focuses on molecules like NAD, a coenzyme that helps repair DNA and regulates cellular energy. As we age, NAD+ levels plummet. Mitochondria, the powerhouses of our cells, begin to fail. Damage accumulates. Systems fail. But in mice, given NAD precursors, cells began behaving like they were young again. Muscles strengthened. Vision improved. Even cognitive function rebounded. It was as if time turned around. Other researchers are experimenting with reprogramming cells using factors discovered by Japanese scientist Shinya Yamanaka. These factors, introduced to mature cells, can erase their identity, returning them to a embryonic-like state, in effect, resetting their biological clock. Its risky, uncontrolled use can lead to cancer, but the promise is profound. The ability to roll back cellular time without altering the calendar, and that leads us to a strange frontier. If biological time can be reversed, even in part, then the arrow of time, as felt by the body, isn't absolute. It's programmable, hackable. We've long known that perception of time is flexible, but now we know that biology's response to time is too. Consider the Toratopsis dohrnii, a tiny jellyfish with a superpower. When injured or stressed, it reverts its cells to an earlier stage, essentially becoming young again. Barring predation or disease, it's biologically immortal. It doesn't defy time, it just rewrites its response to it. So what does that mean for us? Is aging an unstoppable law or a disease? Many in the scientific community now lean toward the latter. Aging is not a predetermined fate. It's the accumulation of molecular damage that might be treatable. If so, then medicine may soon shift from fighting disease to fighting time. Companies like Altos, Labs, and Calico, backed by billionaires like Jeff Bezos and Larry Page, are pouring billions into longevity research. The goal isn't just to extend life, it's to extend youth, the functional years where the body and brain remain sharp. But this raises a deeper question. If we escape aging, do we escape time, or do we merely hide from its effects? We would still exist in a world where entropy reigns, stars still die, universes still fade. But we, fragile creatures built from carbon and memory, might move through time unchanged, like statues drifting down a river that no longer erodes them. Would we be gods or prisoners? Because aging, for all its cruelty, gives life urgency. It forces decisions. It gives shape to identity. The awareness of mortality is what makes meaning matter. If we erase that, what remains? Who are we without the arrow of time whispering, "You must choose"? You don't have forever. Still, the science moves forward, and perhaps the goal is not immortality, but agency, to age on our terms, to hold the pen that writes our story, instead of being pulled by a force we barely understand. And here's the paradox. Even as we chase longevity, we're discovering that time isn't as universal as we thought. It bends near black holes. It fluctuates in quantum systems. It might be different in other universes. It might not even be real. So perhaps aging is not time's triumph over biology. Perhaps aging is biology's misinterpretation of time, a glitch in the code. One we're finally learning to debug, and if we succeed, if we crack the code of cellular time, we'll be forced to ask the most human question of all. What do we do with more time? Strip away the galaxies, silence the ticking clocks, let every motion cease, every atom frozen, every heartbeat stilled. Now ask yourself, without change, does time still exist? For centuries, we've treated time as a given, a backdrop, a flowing river in which all events are suspended. But, in the minds of a growing number of physicists and philosophers, a radical idea has taken root that time, as we know it, may not exist at all. It's not just a poetic musing. It's the result of a crisis in modern physics. Our two greatest theories, general relativity and quantum mechanics, describe the universe with stunning accuracy. Yet they are fundamentally incompatible when it comes to time. In Einstein's general relativity, time is part of the fabric of the cosmos, elastic, affected by gravity, and woven into space itself. It's continuous, smooth, a coordinate. But in quantum mechanics, time is different. It's not dynamic. It's treated as an external parameter, something that flows uniformly and independently, untouched by the dance of particles. Time doesn't curve or stretch. It simply is. This conflict becomes unbearable at the extremes, like the singularity at the heart of a black hole or the birth of the universe. There, our equations break down. Time either becomes infinite or ceases to make sense to unify these theories, to create a true theory of everything. Some physicists have suggested that the problem isn't the math, it's the assumption. What if time is not fundamental? What if it's an illusion, an emergent property, like temperature, that only arises when we zoom out? One of the strongest voices behind this idea is physicist Carlo Rovelli. His work in loop quantum gravity, a candidate theory for reconciling gravity and quantum mechanics, suggests that time is not a backdrop, but a construct, something that arises from the relationships between quantum events. In this view, the universe is not a film reel. It's a mosaic of interactions. And what we call time is just the pattern those interactions make when viewed from the inside. It's like a melody that only exists when the notes are played in sequence. Without a listener, without motion, there is no song, no time. Rovelli writes, "We do not live in time. We live in a timeless world." If that's true, then our experience of past, present, and future isn't a reflection of reality. It's a story told by consciousness, a survival mechanism, a simplification. After all, the brain doesn't detect time. It detects change. Light, heat, movement. Then it orders those changes into what we perceive as a timeline. But that ordering may be arbitrary. Quantum experiments have shown that the order of events can be indeterminate, that two particles can influence each other even when there's no clear before and after. In one 2019 experiment, scientists used a quantum switch to place two operations in a superposition, meaning the sequence in which they occurred wasn't fixed. Event A and event B happened without a defined order. That's not just weird. That's a direct attack on the idea of time itself, and yet we feel it. The ticking of the clock, the ache of memory, the fear of endings. So what is it then? One possibility is that time is an emergent dimension, something that arises from entanglement. As particles interact and become correlated, a direction of change emerges, not as a fundamental rule, but as a statistical preference. Time, in this model, is like a rainbow. It appears real, it feels real, but it depends on perspective, on your position in the system. Move differently, and the illusion disappears. So where does this leave us? If time is not real, what becomes of causality, of morality, of meaning? Do our choices matter if all moments already exist, eternally locked in a timeless structure? Or do they matter even more because we're the ones who create the illusion of motion? Physicist Julian Barber suggests that instead of time, we live in a vast configuration space, what he calls Platonia, a realm where every possible state of the universe exists timelessly. We don't move through it. We are drawn to certain configurations by the structure of physical laws. Our lives, then, are not journeys. They are shapes, still frames, islands in a sea of possibility, and yet we feel them unfold. That feeling, the experience of now, may be the most precious illusion in existence. So here's the final question. If time doesn't exist, why do we feel it so deeply? Why do we mourn the past, fear the future, and clutch so desperately to the present? Perhaps because, even in a timeless universe, consciousness is time's echo, the final trace of motion in a world built from stillness. We are, in the end, not creatures of space, not even creatures of time. We are creatures of change, and change, real or imagined, is enough. We chase time, measure it, fear it, yet barely understand it. If time is just a shadow, then what are we? Travelers in a dream, flickers in a frozen sky. Comment your theory below, because maybe, just maybe, the next great discovery won't come from a lab, but from our mind watching this video right now.